High-temperature systems tap fluids at very high temperatures, typically higher than 150–200 degrees. Because of their very high temperatures, fluids are very mobile, and these systems are also named convection-dominated systems. The main product of a high-temperature system is electricity, which can be transported over long distances and is therefore a very valuable source of energy. Localities with such high temperature are not found everywhere, but they are very apparent, and most of them have been spotted already a long time ago. Everywhere you see surface manifestation of these high temperatures: geysers, fumaroles, hot springs, water with a characteristic sulfur smell. A very dynamic environment indeed. If you look in detail, you can see widespread mineralization, often with striking colors. Surely these fluids must be chemically quite special. Mining was and is frequently associated with these settings. High-temperature geothermal systems are characterized by gradients which are much higher than normal. The curve shows the gradient in Sul-Sanforé, which was the first place where enhanced geothermal system was successfully implemented. The hydraulic stimulation, however, caused induced seismicity, which led to strict controls on injection pressures. Important knowledge has been gathered in Sul-Sanforé, which is now applied in other geothermal systems. Temperatures in Sul-Sanforé only gradually increase with depth, and you need to get to roughly 4 kilometers depth to find temperatures of about 180 degrees. Iceland has a very different profile, with temperatures rising rapidly in the upper kilometer and then further increasing, although at a slower rate. At around 3 kilometers, the thermal gradient increases dramatically. We are not far anymore from the underlying magma chamber. Even more extreme is the gradient in Larderello, where you have temperatures above 200 degrees already at a depth of less than 1 kilometer. The blue dashed curve indicates boiling temperatures with depth. As you see, they increase with increasing pressure. Clearly, temperatures in all three localities are well below the boiling curve, showing that H2O will be in the fluid state. As soon as you drill a well, however, the pressure drops and the liquid water will be transformed in vapor, which will rise to the surface and used in the powerhouse to the surface to run turbines. The geothermal gradient needed for high-temperature geothermal systems are found in two end-member settings: regions with experienced extension and regions with intense magmatism. There are also regions where both extension and magmatism occur, and are very productive geothermal systems are located. The high geothermal gradients in extensional settings are associated with a crustal lithospheric thinning taking place during stretching. As a result, the base of the lithosphere rises closer to the surface, increasing the thermal gradient. This is particularly true for narrow graben systems such as the Rheingraben and the East African Rift. Geothermal fields in Kenya, for instance, are associated with these structures. In the landscape, you can see clear normal faults bounding the more depressed areas and flanked by high reliefs. Hot springs are found all along these fault escarpments. When extension continues, the lithospheric plate breaks and two plates form, separated by a plate boundary where divergent movements are associated with intense magmatism, leading to the continuous formation of new oceanic crust. While most of these ridges lie below 1 or 2 kilometers of water, this is not the case for Iceland. Here, a deep hot spot has uplifted the oceanic ridge, which is now exposed, forming the island. The landscape of Iceland is something geologically speaking very special. Flat-lying basalt flows interrupted by volcanic edifices and sharp and long extensional structures. Areas of intense magmatism can provide conditions ideal for high-temperature geothermal systems. Here, large bodies of magma can solidify close and at the surface, releasing huge amount of heat. Subduction zones are areas of very intense magmatisms. When fluids transported by the subducting plate reach depths of about 100 kilometers, they are squeezed out, rise in the overlying plate, thereby dramatically lowering the melting point of the rocks and generate a large amount of magmas. Driven by buoyancy, magmas move upward, forming complex systems of magma chambers and related feeding dikes, heating up huge volumes of rocks. The ring of fire all around the Pacific subduction zone is a zone of extensive magmatism and huge potential for geothermal energy. When a magma body is in place at shallow depths, it will cause major disturbance of the existing thermal field. The rise of the magma bubble through the crust is typically associated with strong faulting and fracturing, resulting in irregular temperature gradients and developing efficient pathways for meteoric fluids to enter the subsurface and for gases to escape from the magma. Once the magma slows down and stops, it will start cooling down, and within a couple of hundreds of thousands of years it will solidify completely. During this process, gases located loaded with chemicals will be released from the magma chamber, often resulting in spectacular mineralizations and ore deposits. These gases can be very aggressive and dangerous. Let us give a brief look of how temperature geothermal systems function. In the image, you can see a graben-like structure conditioned by normal faults. Meteoric waters enter into the earth mainly along faults, reaching deeper levels, become much hotter, moving along fractures and fluids. Pressure drops related to drilling will further enhance fluid movement, creating a major advective system. In the diagram to the right, you can track the heating path followed by the fluids. Note how the upward fluids typically cross the boiling curve, by which the liquid water becomes vapor, a phase very efficient to use to produce energy. In some cases, especially when temperatures in the aquifer are not that high and permeability too low, then techniques can be applied to enhance flow. These are, for instance, pressure and chemical stimulation, and all fall under the collective term of enhanced geothermal systems. When the system produces only vapor, the steam is used directly to drive turbines, generating power. As the steam expands and cools, it condenses to water, which can be then re-injected in the reservoir, also to maintain the system pressure. If it also contains water, then it is first passed through a separator to remove the water. Dry steam is used for the turbine, and together with the water injected back into the aquifer. If it is warm enough, the water can also be used for heating purposes and transported to a customer nearby the plant. As you can see, high-temperature geothermal systems are able to produce electricity and heat at the same time. Production continues around the clock and is not intermittent like wind or solar. Geothermal energy is therefore not only a clean form of energy, but it forms also the base load, compensating for the fluctuation inherent in other forms of renewable energy.